Welcome back to this lecture on challenges and opportunities in additive manufacturing. As I have explained in the previous lecture that I will be covering a few topics under this series of lectures. So, in this particular lecture I will be mostly focusing on the 3D printing related challenges, right. Not only extrusion, but also other 3D printing related approaches, challenges. In the subsequent lectures, essentially I will be showing you my thoughts along with some of the literature studies on the exploiting AI ML approaches or additive manufacturing of structurally complex implants and so on and so forth. So, the tissue engineering as a subject was introduced to you much earlier in this particular course, and also 3D bioprinting has been mentioned very clearly with lot of examples. So, essentially if you recall, 3D bioprinting essentially means that it is a layer by layer manufacturing of materials containing biological cells or biological macromolecules in a manner that one can essentially maintain the viability of the biological cells or do not compromise on the biological expression of those macromolecules along with the materials when you are going to print it. Okay. So, essentially the printing process do not compromise the viability or biological expression of those either biological cells or macromolecules. So, this is one such examples of the urological treatments for replacement tissues. You have urinary bladder graft, for example, one is to use either urinary bladder graft or urethral graft and so on. So, it has in some specific urological system has a specific tissue structures which are lined up of the organizations, architecture of the cells and tissues locally. So, what are the challenges in this thing? The challenges in the whole urological tissue engineering, like inhomogeneous distribution of cells, it is not patient specific, and poor control of the scaffold microarchitecture. And advantages, it should be easy control over scaffold microarchitecture and porosity. Your conventional manufacturing can be either electrospinning based techniques for fabrication of nanofibrous scaffold, or it is like a 3D bioprinting strategy. So, essentially you give it is an input on the design, then you have a pressure control, then you have a bioink, as I said biomacromolecules, biomolecules or polymeric hydrogels plus polymeric hydrogel, and then you can print the urological graft. So, this is that kind of approach that has been mentioned very extensively in one of the review papers published by Sulov from our group in Journal of Materials Research more than 3 years ago. So, if you see that some of the apart from some of the techniques which I have covered during the earlier lectures, there are also other techniques which has essentially gained lot of interest in the community. One of them is stereolithography, another is digital light processing DLP, and then third one is a multi-photon lithography. Now, this is the essentially stereolithography, this is the DLP, and this is the multi-photon lithography. So, what you see in the stereolithography, you have a UV laser system, these optics are being guided in the mirror scanner, and these are polymerized structure which is getting built in a layer by layer manner in this way. So, this is the building platform, this building platform essentially is immersed in a polymerized structure and there is a coater there. In the DLP technique certainly is much less explored than the extrusion printing. You utilize a photoreactive regime and then you have a UV projections, this is a digital mirror device, and this digital mirror device, this UV projection, UV things is being guided, and there again you have a layer by layer way of making the structures, and then you make these total structures. This is a multi-photon lithography technique. You have a XY movable stage and you have an objective here. So, here you use not the UV projector or not the UV laser, but it is a femtosecond laser. Now, femtosecond laser goes through a optics and scanning system, then it can be focused, and there you can make a much complex structures in these things. All these techniques has its own specific advantages, but at the same time they have specific challenges in terms of the large buildability of the structure, and also their ability to make complex structures with very different shapes, and with very different shape functions and so on. So, this is another way. This is the extrusion based bioprinting technique. Now, extrusion based bioprinting techniques, it can be used for the direct writing. So, you essentially make a filament, then directly write. Then printing in coagulation bath, this is also another technique. Printing in support bath, and this support bath can be granular or colloidal, and coaxial extrusion. Coaxial extrusion means this is one type of you use the cross linking agent here, and the coaxial extrusion means essentially both the strands, they are mixed and then they are extruded in this extrusion based bioprinting techniques. Now, in all these techniques, there are two things that are important. One is the sizes of the structures, resolution and sizes. Resolution can go down to very low, like 100 nanometer and so on, but at the same time volume of the structures that can be essentially built by these techniques, that also needs to be considered. What you see in these three techniques, they have almost like it goes kind of this kind of arrow, like your resolution is increases as well as the total build size also increases. So, laser bioextrusion printing or extrusion bioprinting, inkjet printing, and LDM, essentially liquid deposition modeling. So, liquid deposition modeling, this is also another technique which allows you to build large structures. Okay. And these large structures is like 1 centimeter cube to 100 decimeter cube. These kind of large structures can be built. So, this essentially ensures very good buildability of the structures. But if you look at the resolution, it is 200 micron. Here you can go to laser bioextrusion based printing, you can go up to 5 micron, right. So, if you go to higher, so if you want to have very fine structures, but then buildability will be compromised. If you have relatively coarser resolution like 200 micron, so then buildability is up to 1 centimeter cube to 100 decimeter cube, that you can do. Now, one of the techniques that I have not covered at all in the previous previous lectures, and I thought that this is the relatively less explored 3D printing techniques, is the melt electrowriting. So, electrospinning, for example, as a technique which is used for ultra fine diameter fibers in a chaotic. So, it is a dynamic manufacturing technique, electrospinning, that produces ultra fine diameter fibers in a chaotic deposition technique. Now, what if the placement of every single electrospun fiber could be predetermined, and what if manufactured construct could reach millimeter volume while maintaining accurate fiber placement? These are the two questions. Now, while addressing these questions, people have developed melt electrowriting MEW as a technique, and this as actually can achieve you can achieve this with a solvent free manufacturing approach. So, what are the different environmental variables, that is humidity and temperature, and what is the solution variables? Solution variables is concentration, conductivity, molecular weight of the gel, viscosity, molecular structure, solvent volatility, and molecular weight. Now, this is the electrospinning technique, and what are the variables of the electrospinning technique? Here, what is the distance between the collector and electrospinner? What is the accelerating voltage that you are applying? what is the flow rate of this particular unit and what is the collector that you are using. And typically this is the scanning electron microscope image. What you can see, these fibers, they are oriented in different manner. So you can have fibers oriented in a specific, in a particular orientation, or in most cases you get randomly oriented fibers in these particular cases. Now, if you see that fused deposition modeling, in the fused deposition modeling, you can also get that aligned fiber deposition, but in all these cases fused deposition modeling, melt electrowriting and electrospinning, essentially we use polymer melt, either precursor or polymer melt or polymer solution. And in case of melt electrowriting, we use essentially spinner rate, like high voltage is applied and then charges are generated, and in a collector plate these thin fibers are kind of generated. In the electrospinning you get much coarser fibers and random fiber deposition. Now, if the question that should arise that then what is the difference between electrospinning and melt electrowriting. So, in case of MEW, it is much finer sized fibers are deposited compared to ES, compared to electrospinning. Okay. So, this is very important that you get much coarser fibers here in electrospinning, and melt electrowriting it is much finer fibers that are being generated. Now, if you look at this particular video taken from Nanoscience Instruments, this is without voltage, and with voltage you can see very clearly that filaments are being generated. So, definition wise, melt electrowriting is an additive manufacturing technique that integrates electrospinning and 3D printing to create high resolution polymer fibers. It uses electrostatic forces to stabilize a molten polymer jet to precise layer by layer deposition onto a collector, resulting in scaffolds with customized microstructures, right. And high voltage electrode and this polymeric melt, if it is pushed through, and you can see that polymer fibers are being generated, and these polymer fibers are being generated, and this is the electric field that is being created, and then according to the collector movement these polymer fibers will be deposited on the collectors. Now, if you look at the process little bit more finer way, now you can see that in the electrospinning chamber you can essentially control both temperature and humidity. This polymer solution is being injected through a nozzle here, and these fibers are going there, right. So, this is a E1 electric field, this is a E2 electric field. The difference between that, it is essentially this voltage, this E1 electrode 1, electrode E2 electrode 2, and there is one of the things that is very important is the Taylor cone that is being formed in this particular case, and the Taylor cone near field electrospinning, that is 0.05 to 1 millimeter that is being generated, that is X value, distance between the two electrodes, and then fibers are being deposited. There should be a movie now. This is actual operation of the melt electrowriting machine, and this movie was taken in our collaborative work between my research group and Professor Michael Galinski's research group at Technical University Dresden, and this melt electrowriting facility is available in the TU Dresden, which we have been collaborating with. So, this is that polycaprolactone based scaffolds, and these polycaprolactone based scaffolds are essentially have been used for melt electrowriting for a number of years in recent past. And you can see this particular machine can draw these fibers, very thin fibers, continuously without fiber breakage, and they can change the orientation, right, and they can start essentially depositing fibers in a specific angle to this particular case, right. So, this is, and you can see this is the case for the multi-iterated PCL based scaffolds. You can see nice grid structures. You can change the orientation of the grid structure and see for the orientational dependence on the mechanical properties, for example, in this particular case. So, little bit more on the electrowriting, multi-electrowriting, like as I mentioned, there is a voltage is required, temperature humidity is controlled, and you have a distance between the distance from distance with the collector. And then what are the things that are important in the in the scaffolds or the precursor solution? Surface tension, concentration of the second phase or other structures, and then viscosity. And in the spinneret you can see there is a straight jet and there is a rapid whipping and swing and swinging that takes place during this on this path to the collector here. Now, parameter effect on fiber morphology, solution parameters, polymer concentration, polymer molecular weight and viscosity. So, the diameter of the fiber increases with increasing polymer concentration, and increasing the molecular weight of the polymer decreases the number of beads and droplets. So, higher the molecular weight of the polymer, that will decrease the number of beads. If the polymer molecular weight is lower, then those beads, like these knots and beads, like in individual these knots and beads will be more. Increase the viscosity of the solution has been shown to increase the fiber diameter and avoid bead formation. Again, higher the viscosity of the solution, that lesser is the chances for the bead formation. And what are the processing parameters? Applied voltage, flow rate, tip to collector distance, and then diameter of the fiber decreases with increasing applied voltage. Too high a flow rate results in the appearance of beads, decrease in the flow rate and no significant effects on the fiber morphology. Temperature and humidity, that higher temperature results in fibers with small diameters, and circular pores on the fibers are observed in the higher humidity. Now, there are also other things that which are important in the multi-electrowriting, that how the jet is formulated, and that depends on the polymer characteristics, also the heating system like either conduction, convection, radiation, what is the back pressure and what is the spinneret, whether custom made nozzle or the platinum tipped meter size. And this is the melted temperature and polymer flow rate, that is important. Now, in terms of jet trajectory, applied voltage, distance, environmental condition, voltage system is very important. And how fibers are collected, is it collector dynamics and collector material, that is spinning and collector distance. But out of this, I would say this particular set of parameters are very important for the success of the multi-electrowriting of any new system. I repeat, voltage that decreases the voltage or very high voltage, they can consider the arcing. Then pressure, like if your pressure decrease, then thinner fibers, if your pressure increase, then it is a thicker fibers. Collector speed, there is a small lag and there is a large lag in the collector speed. And these are like different parameters that has been mentioned to you, and it is a summary of all the different parameters, like whether solution concentration or orifice diameter. Orifice diameter essentially dictates that what is the fiber size, right. Then temperature, then humidity, flow rate, tip collector distance, applied electric field and so on. Now, in terms of the materials aspect, which are the materials which are useful, that is the low melting polymers like PVA, PEO, PCl. Out of that, I will put a double star to this particular material, PCl. Why PCl I put a double star? When the multi-electrowriting started, and then Paul Dalton, who was that time at University of Würzburg, Germany, now he moved to United States. Paul Dalton actually has done lot of experiments with one of the first machine. He invented the first machine of the multi-electrowriting, and then he used polycaprolactone. PCl is one of the materials which has been very widely investigated. Some of the natural polymers like gelatin, collagen, silk fibrin, these are also natural polymers, these are used. And materials not suitable for melt electrowriting is that high melting points, low viscosities and poor electrical conductivity. These are materials which are not suitable for melt electrowriting. So, materials properties which affect the melt electrowriting processing, one is the viscosity, melting point, electrical conductivity, mechanical properties, solubility, surface tension, molecular weight. But out of that, surface tension is important, very very important. So, I put a star, viscosity is very important, electrical conductivity is also another important parameters. Now, you can see the switches polymers which are printed using the melt electrowriting. I have mentioned to you just 2 minutes ago that PCl based materials which are most widely investigated, and there is a series of papers which started in 2011, more than 12-13 years ago, when this melt electrowriting as a new 3D printing technique was introduced in the scientific community. Now, one of the things that you notice that how many layers they have formed, 50 layers, circular paths, box, 600 layers and so on, 30 layers, 50 layers. So, these are like different number of layers. So, buildability was essentially introduced in this melt electrowriting. And what is the diameter of the fibers? And diameter of the fibers you can see is mostly micron size, like few microns, like few tens of microns, either 15 micron or 21 micron or 60 micron. Sometimes people have developed tubes like 60 micrometer diameter tubes and all that they have utilized, like 30 layers or 20 layers or single layer of 30 micron fibers. So, these are like different kind of materials. Researchers have used PLLA, polylactic acid, then PLA, polylactic acid, PEG, copolymer they have used, and also many other classes of PCl based techniques, PCl based materials that researchers have used. Some of them they have also used the shape memory polymers like TPU, plus urethane, and then polypropylene they have used with some limited success. So, melt electrowriting is one of the relatively unexplored 3D printing techniques where researchers can explore more opportunities in terms of utilizing new materials which can be used for melt electrowriting, so that this can give you very delicate structures or very soft structures which cannot be used, for example, otherwise by other 3D printing techniques. Now, these are like different examples of the melt electrowriting, like researchers predict that melt electrowriting can be used for the biosensors application, wound healing, drug delivery, and also for tissue engineering kind of applications. And these are taken from different snapshots, taken from different research papers which are published using melt electrowriting scaffolds made of PCl. And then you can see that different kind of structures. Here you can see 100 micrometer diameter, here you can see 500 micron diameter. So, large structure melt electrowriting scaffolds can be used. And here you can see that how cell culture studies were done, and then you can see that cells have proliferated very well on this kind of structures. In some of the cases it is not a straight line kind of fibers, but it is more like a wavy type of fibers, and this wavy type of fibers can be manufactured in this melt electrowriting case. So, in the melt electrowriting there is a concept of critical translation speed. Critical translation speed means what is the speed that the collector essentially will move, will translate, and how that will impact on the quality of the melt electrowritten fibers. This has been investigated to some extent, and in one such papers which is published in Advanced Healthcare Materials, you can see that is the typical electrowritten setup. It is T is less than 270 degrees Celsius. So, polymer which melts at less than 270 degrees Celsius, which is melted, and then you can see this kind of x motion and y motion, you can get the fibers, right. So, essentially it is either going these directions or going these directions, and this is like V naught is equal to V z, that is roughly equal to, or V c is greater than V z. So, with increasing collector speed, what you can see, there is a straight fibers that is kind of formed as 330 millimeter per minute. So, 330 millimeter per minute, if the critical translation speed, anything less than that, you can see such kind of wavy, you cannot get a straight, anything, and then this is the minimum, and here in 320 again you can see there is one kind of fiber, there is a kind of this wavy kind of structures. So, if you want to have a very straight line kind of a fiber structure, and then what is the minimum speed that is required, and in this particular case they have shown that it is like a 330 meter per second. So, to sum up, melt electrowriting is one of the promising 3D printing technique, which has been relatively less explored, certainly compared to the 3D extrusion printing or some of the metal printing techniques, and which holds promise, like to show the capability of one of the variants of the 3D printing, as how this 3D printing technique can be used to make the fibrous scaffolds of different kind of architecture and also different sizes, and then how many layers you can print it using the melt electrowriting. As I said, that polycaprolactone is perhaps the most well investigated material. Whenever people recall about this, whenever researchers mention the melt electrowriting, but there are plethora of other polymers which may be explored in recent, or which should be explored in the near future, so that we can expand the capability of this melt electrowriting beyond polycaprolactone, and that is one of the primary challenges. Secondary challenges is that every 3D printing technique, we develop some kind of process maps, and these process maps allows you to put the printability and buildability of the different materials in some parametric space. So, this here in this particular parametric space can be either voltage in along the, let us say, y axis, or translation speed of the collector may be x axis, or it can be, this is kind of a printing related parameter, or it can be simply materials related parameter, like for example viscosity, surface tension, or electrical conductivity. So, some of these parameters can be plotted along y and x axis, and you can put the different melt electrowritable polymers which people have printed in this parametric space, and then they can see that what are the kind of polymers which can undergo melt electrowriting to provide a very stable, smooth and clinical application specific structures using this melt electrowriting technique. So, I stop here, and then I will continue in the next lecture again on the challenges and opportunities of the additive manufacturing. Thank you.